me just give an introduction and then you can go through that. So
Sure.
Hello, everybody. Welcome to the basically 6 lectures of the school on secure computations. And this is the second lecture of the FHE. So today we have this pleasure of have Ilaria as a lecturer in this session. Ilaria is a researcher in cryptography, specialized in homomorphic encryption. And currently, she is the director of the research at Zama, quite known company in fully homomorphic encryption, located in Paris. So she studied mathematics at a young age in order to basically get closer to cryptography, and notably co-authored TFHE, that today she will talk about that. And it's currently one of the fastest homomorphic encryption schemes in the world. She's the co-author of several publications and the winner of the Best Paper Awards at ISC 2016, as well as the IDash computation in 2019. And before joining basically Zama, I remember that I had this chance to be basically office mate. She was a postdoc here as well, and also was visitor at Microsoft Research. And she did her bachelor in Cagliari, if I'm correctly pronouncing it, University, and master in Joseph Fourier University in Grenoble, and a PhD from Versailles, Paris scale. I mean, if I'm pronouncing it, sorry if it's not
no worries.
pronunciation. Yeah, university. And this is a great pleasure to have her here. Thanks, Ilaria, the stage is yours, please.
Thank you so much. So thanks, Karim, for and Adi for inviting me. It's a pleasure for me to be here. Yes, I will talk about homomorphic encryption. I know that Hilder, that was right before me, did an introduction on homomorphic encryption. So there will be some stuff that you already saw in Hilder's slides, probably. Yeah, I will focus more on the scheme TFHE. I will finish with some applications. And I suppose John Kuhn will talk about applications. I don't know if it's later today or tomorrow, but the first talk on FHE will be her talking about applications. I organized the presentation in this way. I will introduce homomorphic encryption, talk about TFHE in general, a little bit showing you the ciphertext, the different open applications. So generally, after every section, I will try to stop to take questions. But if there is anything that is unclear, even when I'm presenting a slide, please ask the question, and I will try to check on the chat that I see in my screen here. If I don't see the question, if somebody can unmute and ask me the question, it will be amazing. But yeah, don't hesitate to ask questions if something is unclear during the presentation. Okay, so I will start with homomorphic encryption. So I will repeat probably lots of things that Hilder already said. But yeah, what is fully homomorphic encryption? Well, it's a very, very nice technology. I hope you will enjoy those talks on homomorphic encryption, because it's really a beautiful technology. And it's like cryptography in general. It allows us to encrypt the messages. So in my slides, you will see those messages, in this case, X inside the boxes, which have a lock on the bottom or something different, but boxes, let's say. So they allow you to encrypt and decrypt messages, but apart from that, they also allow you to do operation on ciphertext. So if you have two encryptions you have two ciphertext encrypting message X and Y, you can add those ciphertext together, and the result is going to be a new ciphertext encrypting the addition of the original messages. And you should do the same with multiplication. So, of course, the operation on the plain text, so X and Y, it's traditional addition and multiplication as we know them. But the operations on the ciphertext might be different, because we're working with something that is not always just an integer, or the operation can be something different. But the important fact is that whatever we perform this operation, the result is what we care about. So we had homomorphically to ciphertext, so we multiply them homomorphically, and the result is going to be a ciphertext encrypting the addition or the multiplication of the inputs. And so, of course, we want to do something more than just additions and multiplication. We would like to combine additions, multiplication, or even potentially other functions in order to possibly evaluate any functions we have in mind, from the most simple one to the most complex ones. And so if we're able to really evaluate any function, is that what we call fully homomorphic. And the message can be very different data types. So they can be bits, they can be integers, they can be reals in a fixed interval. And the encryption can be secret key or public key encryption. It depends on the flavor that we want to give to our schema. And of course, the decryption is always done with the secret key. This is mandatory, of course. So yeah, that's it. I think this you know already, thanks to Hilder. So what is the interest of homomorphic encryption in real life? Well, especially in this period of time where we interact a lot with this cloud entity, everybody of us has probably an email or a social networks account, or stores photos and documents on the cloud. So we have very often this scenario when we are the users on one side and we interact with the cloud for whatever reason we want to interact with it. And generally, yeah, we send information to the cloud stores it or manipulates it in a certain way, and it sends the information back if we require it back. So as instance, I don't know, you want to apply a filter to a picture, you put the picture on a server online, on a service provider online. And the response you have is your picture filtered. So this is a little bit what the message, the function means. So the message can be any data that you send, and the function will be any operation that the cloud could apply on your message, depending on what you asked, of course. So with classical crypto, what happens is that the communication is encrypted. So you can send a message encrypted, and you will receive also the answer to your question encrypted. But in order for the cloud to perform this modification on your data, the cloud needs to be able to access the data in clear. And this is a bit annoying, especially when this data that you're sending is sensitive data. And for sensitive data, I mean health-related data, financial data, genomic data, everything that you can imagine, every data that you possess and you don't want to share with random people, with anybody. And this is sensitive, and you want to keep it private in general. And so thanks to homomorphic encryption, this is now possible because you don't, thanks to homomorphic encryption, you can encrypt not only the data during the communication, but you can allow the cloud to manipulate your data without having to see the data in clear. So in practice, the cloud doesn't need to open the ciphertext. It can apply the function on top of your encryption, and the result is going to be encrypted. And since you are the owner of the secret key opening this encryption, then you are the only person that will see the result. And so the cloud will learn nothing about your data. There will be no data breaches in practice, because even if an attacker enters the cloud and tries to steal the data, the only thing it will steal is going to be encrypted information, so something that looks completely random. And also the server location, so the physical location where the cloud is in the world, will not be relevant. So the physical location is important because depending on where the cloud is located physically, different regulations in terms of legal regulation will apply on the data that is in the server. So I don't know, in Europe, as instance, we have GDPR regulations that protect the privacy of data, but in different countries, there are different rules or there are no rules. And so sometimes we don't want to access a service in a certain country because we don't know about the privacy regulation on the data in this country. Well, thanks to homomorphic encryption, we don't care anymore, because even if we send the data into a country where there is no protection on your privacy, well, the encryption should be the thing that is protecting your data. So you don't need anything else to protect your data. And so your data remains private all the time. Okay, so this is very nice. seems to be a very nice solution to many real-world problems. But homomorphic encryption is, seems nice to describe, but it comes with little, let's say, issues. And the major issue is what we call the noise. So again, probably Hilder told you already about it. So the noise is some quantity of some randomness that we put inside the ciphertext in order to protect its security. So when we encrypt the ciphertext at the beginning, we need a little bit of randomness that I will measure with those thermometers next to my ciphertext. And the problem of this randomness is that, yes, it's important for security, so it's mandatory to have it there. But the problem is that every time we perform an operation, this noise starts growing. So when we do additions, it grows a little bit, but when we do nonlinear operations like multiplication, it grows a bit faster than addition. And the problem is that if we start combining operations together, so perform additions, multiplications, addition, multiplication, and so on, at some point, this noise will reach this red limit, this red bar. And once it arrives to this red bar, the decryption is not correct anymore. So we need to be always careful in order to keep a noise under this limit. Otherwise, our computations are incorrect. And so there was a solution. Initially, this was a hard problem to solve, but in 2009, a researcher named Gentry found a solution that is called bootstrapping that allows us to deal with this noise growth. So the bootstrapping is it's a complex operation. We will see later in my slides the description of the bootstrapping in TFHE. But the concept to explain bootstrapping is actually very easy. So I will try to show you with images how does it work. So imagine that you have a ciphertext where the noise has already reached the limit. So if we do even another operation, we risk to destroy the message. So at this point, we want to get rid of the noise. And in general, to get rid of the noise, what you do? You should decrypt because decrypting allows you to get back X and eliminate everything that is related to the encryption. So decryption gets rid of the noise. The problem is that for decryption, we need a secret key. And so if it's the cloud that is doing those computations and the cloud needs to do the noise reduction without our help, we cannot give the secret key to the cloud, because if we give the secret key to the cloud, well, it just decrypts and finds the message. So why we encrypted in the first place? And so the Gentry's idea is to do decryption, yes, but to do it homomorphically. So what does it mean? It means that it takes the first encryption, this X encryption, this encryption of X, this blue encryption of X, and it puts it inside a new ciphertext. So this encryption becomes the new message. So it's a big message, but it becomes a message. So now, since this is the message, the noise didn't change because we didn't touch the ciphertext itself. We just put it inside a new ciphertext. And this new ciphertext is homomorphic encryption. So there is, of course, noise at the beginning, but it's a small noise, so that is there for security reason. So now we want to open the blue ciphertext inside the green one in order to protect the message all along the way. And to open the blue box, we need a blue key. So the decryption is actually open in the blue box. And in order to decrypt, well, we need the blue key, but we cannot give the blue key in clear. So Gentry's idea is to provide what he calls the bootstrapping key. So it gives the blue key, but encrypted inside a green box. So now that we have the encryption, the blue encryption inside the green box, and the blue key inside another green box, and those key encryptions are homomorphic, we can perform the operation decryption inside the green box. And so in practice, we open the blue box inside the green one. The noise of the blue box goes away, so we forget about it. And what remains is just X encrypted inside the green box. Now, what happened to the noise of the green box? Since this is an homomorphic computation that can be additions, multiplications, or something else, this noise has grown compared to the beginning. But if we are able to manage parameters in order to have, after the bootstrapping, a little bit of space in this thermometer to perform at least another computation, then we won the game, because we can perform computations until this noise reaches the limits. And as soon as the limit is reached, go back to this point, perform a bootstrapping, reduce again the noise, and continue performing computations. So in practice, you will perform computations, homomorphic computations, additions, multiplications. As soon as the noise reaches the level you bootstrap, you can start again with computation, you bootstrap, and so on. And so in practice, you can evaluate any possible function because you don't have any more limitation imposed by the noise. So now this is a very elegant solution, but it's very, very expensive.
Ilaria,
Yes.
sorry, before moving
Yes.
to the next slide, there is one question. Asks that,
Yes.
can we encrypt a key with the same key itself, basically?
Yes, we can. We can encrypt the blue key with a blue key if we want. Generally, what we do in practice is that we have a set of two keys, a blue and a green one, and we encrypt the blue key with, actually what we perform is what we call a key switching that allows us to change the key. But well, to make the story easy, yes, you could encrypt the blue key with itself, or you could create a chain of several keys that encrypt one each other. And so you kind of have a circle of keys. So you go to the green, and then you come back to the blue, then you go to the green, then you come back to the blue, and so on. So yeah, this is called the circular security. It's in theory, encrypting a key with itself or creating a circle of keys, it's okay in terms of security. So the answer is yes, you can.
Okay, thank you very much for a great explanation.
Thanks. Any other questions on the bootstrapping part?
I don't see anything in chat, but please, if you have a question, raise your hand and I will unmute if you are lazy enough to in the chat. So
okay, I will continue for now.
Yeah.
So, but if there is question, yeah, please interrupt me.
Sure, thank you.
It must be KDM secure. What is KDM?
Yeah, can you explain yourself a little bit? What's this KDM you mean? I mean, abbreviation? It's
Key dependent message. What does it mean? I'm not sure I understand this notion of security notions. So the message of the key inside the message is key dependent. Yes, of course, because it's key. So yes, it should be key dependent, KDM secure, I suppose.
okay, thank you.
Okay, sure. Perfect. So again, bootstrapping seems very nice, but it's very costly. So sometimes we can ask ourselves, well, it's really important to do bootstrapping all the time, or we can avoid bootstrapping. So the answer is it depends. And it depends in practice on the circuit you want to evaluate, the function you want to evaluate. So the point is, I have this rule of thumb that I think it's let's say an easy way to understand if you can if you should you can avoid bootstrapping. And so the idea is the following one: if your circuit, so if the function you want to evaluate on your data encrypted, it's a small circuit, so you have very little number of operations, and especially if it's known, if you know how many operations you wanna perform, and these known operations are not so many, then you can use what is called a level approach. So you don't need to do bootstrapping. You set up the parameters, or if you want, you set up your thermometer to be big enough, and so you will measure how much noise those operations will add in your thermometer, and you make sure that there's enough space in your thermometer to perform those operations. So this in practice means making the parameters large enough to support all those operations. So you don't have to do bootstrapping, and those operations can be done easily, let's say. But if on the other side your circuit is very, very deep, so you have many operations, or if it's even unknown, because sometimes when you send your data to the cloud where you ask for a service, but you don't know how this service will be done. If you send a picture and you ask to apply a filter, you don't know exactly what is how mathematically you can express this filter, right? So you don't know how many operations the cloud will perform on your data in order to send you back the answer. So in this case, if the circuit or if he knows or if she knows that the circuit is very deep, so it contains many operations, then what is better to use a bootstrapping approach. So you will do operations, and from time to time you will bootstrap, so you're sure that the noise will not be a problem. And so what happens if the circuit is very deep but known? You might think, well, maybe we can use a leveled approach where we'll make the thermometers big and fit all those operations inside. Well, the problem of an approach like this is that every time you make the parameters grow, if the circuit is larger, the parameters need to be bigger. And if the parameters are bigger, the operations are more costly. So you not only have more operations because your circuit is bigger, you have to perform even more costly operations. And sometimes, if the parameters grow too much, it might be possible that a computer or a server is not able to support those operations, or it becomes so inefficient that actually performing bootstrapping is better. So the suggestion in general is that if your circuit is very, very deep, so if you have really many operations, especially multiplicative depth of the circuit is huge, it's better to use the bootstrapping approach. So you keep your parameters reasonably small. You have to perform this bootstrapping that is costly from time to time, but it still will be more reasonable than performing very, very expensive computations in a leveled approach. So yeah, that's a little bit the idea. And so what happened in the last 40 years? So Gentry proposed the solution, and what do we have right now? Do we have schemes that we can use? So again, probably Hilder show you something, but I tried to summarize this in a 40 years timeline-ish. So in 2009, we had the solution proposed by Gentry. This was really impressive solution because it was 30 years, about 30 years, the researchers were looking for such a solution. So in 2009, we have his first proposal, but Gentry's proposal, even if very elegant, was inefficient and actually later was even broken in terms of security. But after Gentry proposed this solution, researchers got really excited and started proposing lots of results. So we had the first, in 2010, we had the DGHV, the proposal by Van Dijk, Gentry, Alevi, and Van Kutanatan, which was a scheme based on a lattice problem called the approximate GCD that works over integers. So this scheme is very, very nice, but is less used than other schemes nowadays. A scheme that we still use today, and that gave birth to a very nice which is based on a problem called LWE that probably Hilder described, I will describe again in a few slides. And this scheme is very efficient for level operations, but the bootstrapping is not super efficient. So bootstrapping can be done, but we prefer this scheme in a leveled approach, let's say. In 2012, there was another scheme proposed, which is LTV, which is based on untrue, and which is another problem on lattices. And I think in the meantime, it has been broken or has a problem in terms of security, so it's not used anymore. But there are new solutions mixing untrue together with LWE that came out in the last few years, and they are really looking very interesting. So untrue is not abandoned completely for homomorphic encryption. It's used mixed to LWE right now. In 2013, so a year later, we have another scheme based on LWE, which is called GSW, which is very similar to BGV, but has some really important differences. These schemes, again, gave birth to another, let's say, branch of schemes that we use nowadays. And this scheme uses larger ciphertext, but it's very scheme based on this. In this one, are very good in terms of bootstrapping, so they perform a very fast bootstrapping. So continuing on the two family, we have a BFV variant of BGV. In GSW, we had the scheme FHE2 that proposed for the first time a very, very fast bootstrapping. And in 2016, we had also CKKS, which is a scheme in the BGV family again. And in 2016, same here, we have TFHE, which was initially an improvement of FHE2, and then he extended on other, let's say, functionalities. And so, yeah. BGV-like schemes and the other one that I call the GSW-like schemes. In BGV, a leveled approach is preferred, even if bootstrapping is possible, but it's very inefficient. While in the GSW family, the bootstrapping is very, very fast, very efficient, and so we prefer a bootstrapping approach. And so in the rest of my slides, I will focus on TFHE as promised at the beginning. I can stop for a moment if there are any questions until here before starting with TFHE.
Yes, I see one hand raised. Yeah, Shahram has a question, so I just give me a second.
Oh, I think it was she was just I think clarifying on the KDM about circular security. No, you have a question. Sorry, I see your hand raised.
Yes, go ahead.
Hello, Ilaria. Thank you for your nice presentation. It was really, really nice, and I liked your last slide about classification of different classes of FHE. I have a question. I don't know if you have seen Gentry's survey paper. There he speaks about 3 generations of FHE. If you have seen that paper, I wanted to know that these branches, which one falls in which generation that Gentry talks about.
Ilaria, you are muted, I guess. Can you hear us, Ilaria? Okay, now it's coming.
Can you hear me?
Yes, now we can.
Okay, I think I lost you for like 1 plain minute.
Okay, so let me repeat my question.
Thanks.
So I said that Gentry has a survey paper on fully homomorphic encryption. I don't know if you have seen it or not. And in that paper, he speaks about 3 generations of FHE. So which the first one is a Gentry scheme. The second generation is this BGV and BFE, and the third generation is GSW. And I wanted to know that if this picture follows the same classification, or is it different?
Okay, so I have to be honest, the generation situation is very unclear to me, because Gentry should be first generation, right? And I think also the GHV gets into the first generation. And then you have BGV and BFV that are considered second generation. Everything that is on GSW is considered third generation, and somebody puts CKKS or sometimes CKKS and TFHE in 4th generation. So for me, it's just like generation came in terms of timing and on variants that were proposed. If you want to give generation names to the scheme, you can. It doesn't change the scheme. It doesn't change the year it came out. So I don't like using the generation thing. But yes, I mean, and I don't know if there is really an agreement in the generations in the end.
Okay,
but
thank
yeah,
you.
Of course, sure. But yeah, it doesn't change much on the scheme belonging to a generation or the other, I would say. Yeah.
Thanks. It was clear. But I like your classification much better. So thank you.
Oh, thanks. You're very nice. Thank you so much. Okay. Any other question?
I don't see anyone. Maybe we can continue if there is.
Okay, perfect.
Thank you.
Okay, so TFHE finally. Again, TFHE is if we go back to this branch, is in what I say the GSW family, but whatever, GSW or BGV, they are schemes based on the problem LWE. So I will quickly describe what is LWE. Again, I suppose Ilder already told you, but let's refresh our mind. So learning with errors, that I will call LWE, and that is generally called LWE, is a scheme, is a problem that was proposed by Regev in 2005, and it's a hard problem on lattices. So the idea is the following one: you take a secret key that it's a vector of n integers. They can be distributed depending on, they can be uniformly random in a certain interval. They can be ternary. They can be many things. But let's say they are integers. Learning with errors. I don't know how much did you hear, but we have a secret. There is an integer vector of elements, integer elements, and what we do is that we choose after choosing the secret, we choose n random elements in ZQ. So ZQ is integers modulo Q. This notation means integer modulo Q. And we choose n integers modulo Q random. And then we also choose a little element in ZQ that generally it's called E, and it's generally a Gaussian error. And then we build a B that is equal to the sum between an inner product in practice between the A elements and the elements on the secret key, and we add the error. So in practice, we have B equal to vector A times vector S, if you want, plus a little bit of error, reduced modulo Q. And so what happens is the following thing. So we keep the secret and the error secret. We don't reveal them. And we reveal the A elements, the random elements, and the element B. And we call this thing LWE sample. So now, the LWE problem says that if we give many LWE samples, so elements, vectors build in this way, or we give many elements that are completely random. So we take the A elements are random, but instead of putting B built this way, we just put another random elements. It's hard to distinguish the samples, the LWE samples from uniform. So in practice, it means that those samples, those LWE samples, look completely uniform. So this is what is called the decisional problem. We also have the computational problem that says that not only those things look random, but if I give you as many LWE samples as you want, built this way, it will be very hard to find the secret key. So if I give you LWE samples, they are indistinguishable for random, and it's very hard to find the key, the secret key, by looking at them. And so starting from this hard problem that still is considered hard nowadays, we can build a cryptography. So a few years later, there was also a variant of LWE that was proposed. It's called ring LWE. And we also use ring LWEs nowadays. And it's the same thing, but instead of using elements, integers modulo Q, we use polynomials. Polynomial that we will see soon.
So,
okay, so now that we know
LWE, two questions in the chat.
Sure.
So yeah, the first one says that whether the GHV-based FHE are still under research interest in recent years.
Okay, so for the GHV, I think there were some works trying to improve the GHV. I think Hilder has a paper about this. I don't wanna be wrong. I don't know if Hilder is still here, but yeah, there are not many papers on the GHV, but it's not broken. And people might continue doing research, but LWE-based schemes are more efficient nowadays. So I would say that the major focus of the community is on LWE.
I see. And there is the second question that are these LW or ring LW are hard in the standard model of computation, whereas discrete log or some other problems are hard in generic group model? So
LWE is considered hard. It's also post-quantum, so it's hard problem even with quantum computers, let's say. But yeah, I would say, what is the in generic group model? Yeah, I would say yes. They are hard. They're considered hard in the standard model.
Okay, thank you.
Okay, so how do we build a cryptography with LWE? Well, we take, we want to encrypt a message. So the messages that we encrypt with LWE are integers modulo P, with P So yeah, selecting a secret key. So for the rest of my slides, I will use the binary secret keys. So uniform binary secrets. So those elements are bits. And again, we select A elements at random, as in LWE. And we build the B slightly differently. So B is still the product between the A elements times S plus an error. And now we use this quantity to mask our message. And we rescale it by this quantity delta. So delta is an integer known and generally is Q over P. Yeah, in general. So the error is Gaussian and everything is like in the previous slide. This just the difference is that we're using LWE sample to mask a message this time, and this will be the encryption. So when we have this encryption, if we want to decrypt, well, we need to know the secret key. And so to decrypt, we perform a multiplication between A times S and we subtract it to B. So if we solve this equation, you will see that the result is delta M plus the error. And then in order to retrieve the message, and so to get rid of the error, you will divide this quantity times delta, and you do a rounding. So now this works if the error is smaller than delta over 2. So this is, in practice, delta over 2 is your bound on the thermometer of noise. So why does it work? Well, it works because visually you can see it looks like that. You have your message that is in the most significant bits. This is why LWE in the most significant bits. It's rescaled by delta in order to make it, put it far away from the error. And the error is something that is generally in the least significant bits. So the error grows. Every time it grows in this direction, it approaches the message. But if the error is smaller than delta over 2, at the rounding moment, when you do the division by delta and you do the rounding, you should be able to retrieve the message. If instead the error is larger than delta over 2, it will start contaminating, let's say, the message. And so when you do this operation, you will not find the message, you will find something else. And so it's important that this condition on the error is always satisfied. Now, I'm talking about the MSB variant. Why? Because there exists an LSB variant where the message is in the least significant bits and the error is in the most significant part. And this is like some schemes like BGV use this other variant. But for the rest of the slides, I will focus on the MSB variant, and very similar things can be said on the LSB variant. Okay, so now we saw how to encrypt. We saw how to decrypt correctly, and we saw what is the condition on the noise to decrypt correctly. Now we to do homomorphic operations, right? And so with LWE, we can add together two ciphertext by just adding the A parts together and the B parts together. And the result is going to be an LWE ciphertext under the same secret key, encrypting the addition of the messages. So LWE is additively homomorphic. And of course, the noise grows a little bit, but very reasonably. And by just extending the addition, we can see that we can also multiply a ciphertext with a small constant, with a small integer, and this will still be homomorphic. So you will find in output an encryption of the message times this small constant. So why I say small constant? It's important that the constant is small because the size of this constant will affect how much the noise grows. So the largest is the constant, the more the noise grows. So if the smallest constant is small, it's okay. If the constant is large, we will see later what happens. But the point is that in here, we don't have yet a multiplicative homomorphic operations. So we cannot multiply directly to LWE ciphertext. It will not work. It will give us something that is not exactly what we are expecting. So for now, let's say that LWE is additively homomorphic, and we'll try to see later if we can application. Okay, so LWEs encrypt a single message, a single integer modulo P. What about encrypting something more than a single message? What about encrypting polynomials? Well, we can do it with ring LWE. I think I heard Hilder talking about it, so probably you know already. But yeah, let's see how it happens. Ring LWE can be used. So instead of encrypting a message modulo P, we will encrypt a polynomial message with coefficient modulo P reduced modulo xn plus 1. where xn plus 1, n is a power of 2, and this is a cyclotomic polynomial. So this is a very nice polynomial to do operations, so we will see it later. But in practice, what does it mean? This is that we have a polynomial with n coefficients, and those n coefficients are reduced modulo p. That's all. And so the ciphertext, again, we choose a secret key that this time is a polynomial. For the sake of the slides, the coefficients are binary, but this is not mandatory. And we encrypt it by choosing A and B, where A is uniformly random polynomial this time, instead of being a vector of coefficients. And B is obtained by multiplying polynomially A and S, and by adding an error polynomial that contains Gaussian coefficients. So it's like before. Before we had the integers, now we have polynomials. And again, we use this quantity to mask the message. So we rescale the message times this delta. And yeah, we multiply and we use it to mask the message. So now to decrypt, how do we do? Well, it's always the same formula. It's B minus A times S. So if you invert this equation, you will see that this is equal to delta M plus the error. And again, to decrypt, we take every single coefficient of this delta M plus the error, and we divide it by delta and round it in order to retrieve the message. And so as before, if the error is smaller than delta over 2, this should work. So it's like you have to imagine it as if you had like a LWE plaintext in every coefficient of your polynomial message in practice. So it's exactly the same thing as LWE. Is smaller than delta over 2. Otherwise, you compromise your message. And so ring LWE as additive homomorphic property by adding together the A polynomials and the B polynomials. You have a new ring LWE encryption of the addition of the messages. And by extension, if you multiply an encryption with a small constant polynomial or a small constant by itself, this is homomorphic. And this should be small because the bigger is the coefficients of the polynomial, the larger will be their noise growth. And we have to be careful with that. But again, even with ring LWE, we don't have immediately a product that can be performed. So for now, we're still additively homomorphic. We will try to understand now how the multiplication can be done. So before understanding how to do the multiplication, let's try to solve the problem about multiplying by large constants, because for now we can multiply only by small constants. So in order to see it properly, let's take a gamma. Instead of using a polynomial, we will use a very large Q, which is our cipher modulo. And let's try to see what happens if we multiply these larger constants times our ciphertext. So if we do as we did before for the multiplication, so multiply gamma times the A part and the B part, what happens is that the noise will grow proportionally to gamma. And so since gamma is larger as much as Q, or is closer to Q, let's say it's a large constant, the error will grow a lot. And so the message will be compromised. So we really cannot multiply immediately by large constants. So we need to think of alternative ways to perform this multiplication. And so the researchers find a very nice way that is based on decomposition. So it's in this example, I'm putting these constants that are very not nice to see. But what you have to imagine is that you take your gamma, large constant, and you decompose it in base 2 as instance. So let's take beta equal to 2. So you start from the most significant bits. So you take bit by bit the elements of this gamma, okay? So you decompose, and those elements, so if beta is equal to 2, those elements are the binary decomposition of gamma in practice. And so they are just a bit of information. So now, instead of multiplying the gamma i's times an encryption of the message, you multiply times special encryptions of the message, where instead of just having the message, you multiply at encryption time the message times the element of the decomposition base. So in practice, you don't encrypt the message, but message times q over beta squared, q over beta to the power of L. So since this multiplication is done at encryption time, it doesn't affect the noise, because then you add a small noise to it. So the noise is not affected by the quantity here. And when you do the multiplication, homomorphic multiplication between those elements and those ciphertexts, since those elements of the decomposition are small, in our example are binary elements, well, the noise will grow a little bit, but not much, like just a little bit. And then what will be the result? Well, the result will be message times gamma I q to the beta I. And now if you add all of them together, in practice, you are recomposing your gamma constant. So when you add all those things together, the result will be an encryption of gamma m, as we wanted. But since we are doing additions, and addition make the noise grow linearly, the noise, yes, will grow, but it will not, in theory, if you choose your parameter correctly, it will not affect your message. So it will be, the noise growth by using this technique will be way slower than doing directly a multiplication between gamma and the encryption of m. And so in practice, we found a way to multiply large constants times our ciphertexts. Do we have any questions until here?
I don't see anything in chat, anything.
Okay.
And we can continue, I guess. And
okay, perfect. Okay, now why I want to do multiplications with large constants? Because our ciphertexts are large constants. So the elements A, I, and B in your ciphertext are integers modulo q. So they are in practice large constants. So I want to see how I can multiply a ciphertext with another ciphertext that is composed of large constants. So I needed something in order to be able to perform these multiplications in practice. So for the rest of the slide, I will call this special encryption of M, which is a list of encryptions of M multiplied times those quantities, RLEV. And I will immediately use this new encryption, special encryption, in order to explain to you the way to do the multiplication, especially the multiplication that we do in GSW-based schemes. So GSW is the family in my timeline that is on top, the one that has the fast bootstrapping. So in BGV family, the multiplication is done in a different way. I hope Hilda showed you. Otherwise, yeah, we can talk about it. LWE ciphertext or ring LWE ciphertext. We build a largest ciphertext, a really, really huge ciphertext that is called the ring GSW ciphertext. So the ciphertext encrypts a polynomial message exactly like ring LWE, but it's way bigger. So you have to imagine it as a three-dimensional matrix if you want. And this three-dimensional matrix contains many, many ring LWEs inside. So you have ring LWE, ring LWE, ring LWE on top, and then on the bottom, ring LWE, ring LWE, ring LWE. So those ring LWEs here are, in practice, what I showed you before, an RLEV ciphertext. So in practice, a ring GSW is a composition of two RLEV ciphertexts. So it's really a big, big ciphertext. It's huge. And what does those ring LEV ciphertext encrypt? Well, the ones on the bottom encrypts the message times the element of the base, as I showed you before. While the one on the top encrypt not the message, but minus the message times the secret key times this quantity that the decomposition base that I showed you before. So I will try to skip the details, but why is this so important? Why it's important to have this ring LEV ciphertext in here? Well, because when we will do the multiplication, we will need to decompose and recompose one of the ciphertext. So just to skip this slide very quickly, ring GSWs, since they are composed of ring LWs, we can add them together and they are additively homomorphic. We can still do the multiplication by a small constant. So we still are additive homomorphic. But then, yeah, the interesting part is how to use this big structure to do a multiplication. So as I kind of announced before, what you do is that you take the ciphertext, let's say one layer of ciphertext in the first encryption. You perform a decomposition as we did before for the large constant gamma. So you take every single element, every coefficient of those polynomials, and you decompose it with the decomposition base that I gave you before. And after you decompose it, what you do is that you multiply it with the second ciphertext. And this second ciphertext is composed of RLEV ciphertext. And so thanks to the RLEV, thanks to the fact that the RLEV contain the recomposition base, you decompose, you recompose, you can do the multiplication, and so you obtain in output one of the layers of your output ciphertext that this time will encrypt the product between the two messages. And so if you do it for every single layer of the input message, for every single layer you decompose and you multiply 10 times the matrix, decompose and multiply times the matrix, you build little by little all the layers in the output ring GSW. And so in this way, that is not really natural because you are not doing like a direct multiplication. You need to decompose and multiply. But by doing the operation this way, you're able to have multiplicative homomorphic encryption. So with ring GSWs, we can do additions and also multiplications. And so we have all the operations that we wanted to have in order to have fully homomorphic encryption. We just need to think about the bootstrapping, but we will see it later. Okay. I showed it. Yes, Hilder, I can see you. Perfect. Thanks. Okay. Okay, so this is the way we do ring GSW multiplication. And this is very nice because now we have three types of ciphertext. We have in TFHE. LWE and ring LWEs encrypt the first one, a message, an integer, only an integer, while ring LW encrypts a polynomial. They are both additive homomorphic, and they, of course, can be multiplied by small constants, while ring GSW encrypts a polynomial. It's a very, very huge ciphertext because it's like a matrix of ring LWEs, but it doesn't only have additive homomorphic property, but it also can have a multiplication. So this is kind of all the ciphertext that we use in TFHE, and these are their homomorphic properties. So this is, if you didn't, if you, let's say, forgot something in my previous slide, I would say that this is the slide to keep in mind. Three types of ciphertext, integer encryption, polynomial encryption in those two. For those two, you have additive homomorphic properties. For this one, you have additive and multiplicative homomorphic properties. Is homomorphic in different public keys possible? Yeah, you can use different public keys, but you cannot use them in the, how can I say?
Ilaria, we lost your voice and the screen. Okay, now I can. Oh no, I see. She's going to a little bit connect.
Yeah, I think she's disconnected.
Can you hear me again?
Yes, yes. Now
every time I start answering a question, I go away. Sorry. So I was trying to answer the. You can use different public keys, but you have to be careful. So you can use several keys in the same construction, but generally, like when you want to add together two LWE ciphertext, two ring LWEs or two ring GSWs, the two ciphertexts you combine need to be encrypted under the same secret key or public key, whatever. And if you use a different public key, you will do an operation that is called key switching. That is very similar to the relinearization technique Hilder showed you in his presentation. I think this was no, it was not Siva, it was Madhavi. Yeah.
Yes, Madhavi. I see. I guess we don't see any more questions in, at least in the participants. We can continue. Thank you.
Perfect. Okay, so before I move, so now the next step will be bootstrapping. But before I move to bootstrapping, I will just show you a different way of seeing LWE encoding. So I will use a toy example to do that. Again, you can skip this slide if you want, or you can use it to have a different way of seeing things. So before I show you the way the encoding in LWE is done, so you have your 0, you have Q, you choose your plain text module, and you have your delta. And generally what you do is that you put the message in the most significant bit rescaled by delta, and you put the error in the least significant bit. So of course you can, and the error must be smaller than delta over 2. So you can use, if you want, this way of visualizing things, or you can use what I call the torus representation, which also gives a little bit an idea on the name of TFHE, which is torus FHE. So in practice, the same quantities but modulo 64, you can imagine it as a circle that rotates into itself, like a torus, this kind of, circle, a donut, if you want. So you start from 0, you increase going around, and when you reach 64, well, you go back to 0. So this is modular reduction, modulo 64 in this case, but modulo Q in general. So what happens? If you want to see your encoding, so the same thing that I'm showing you here in a visual way on the torus, you can imagine that your messages are put in let's say in intercalated with constant interval, and the interval between two messages is delta. So to have a new message, you have to add a delta quantity. So you have 0 that is at 0 position, 1 that is at 16, so delta, 2 that is at 42, and 3 that is at 48. So the distance between two successive messages is delta, and it's the same thing that you will have in this representation. And when you add the error, it's important that in order to decrypt correctly, your error doesn't pass those red lines. So in practice, it's not bigger than delta over 2, negative or positive. And so when you decrypt, what happens? So when you decrypt in here, you do divided by delta and then rounding. But if you decrypt in the torus, it's just easier to observe where the decryption is. So imagine that when you decrypt, your message is this one, is 53. Well, 53 is here on the torus, right? And what is the closest message to 53 in the torus? Well, 53 is in the slice corresponding to the message number 3. So when you decrypt 53, it should give you the message number 3 as expected during the encryption. Or if you want to do it in an analytic way, you just divide the 53 times delta, which gives you, which is 16, and you round the quantity that you obtain, and you will obtain 3. So to summarize the slides, this is just a way of visualize differently the encoding. So delta times the message plus the error. You can see it this way if you want, or you can see it this way. I really like this way because it helps me later to explain bootstrapping in a intuitive way, I would say. So in this toy example, again, this is a toy example because we don't use a Q equal to 64. It will be probably very insecure. In practice, we use a Q that is equal to 2 to the 32 or 2 to the 64. So we use we encrypt by using 32 and 64-bit integers. So this is really a toy example. It's not 2 to the 64, it's just 64. But yeah, I hope maybe somebody will like this one later in the slides. And
yeah, I can confirm that I already like it, and it's
Thanks.
Similar. Yeah, I mean, maybe I can add this point that we have a similar idea in digital communication that you map to the space, and you want to have a similar idea that once you map to the different points on the space, once you add the noise, you want to be detectable, and here you want to be decryptable almost. I mean, it's a quite similar, analog. Thank you very much.
Thank you, Karim.
Thanks.
Yeah, so the same thing that I showed you in the previous slide for LWE applies exactly for ring LWE. So instead of having just one torus, in this case, you will have n toruses, so 1 per every coefficient, and you have here your delta M0 plus E0, so you have the same idea as before, delta M1 plus E1, and so on. So in the ring LWE is like you have the same encoding in every coefficient, so it's very, very similar. Okay, so before I move to the bootstrapping, I need to build another few operations, starting from the basic operations that I showed you before. And those operations allow me not to mix the keys, but to mix ciphertext encrypted under the same keys. And I don't mean LWE with LWE, but ring LWEs with ring GSW. So start making those 3 different types of ciphertext interact between each other. So the first interaction that we create is what we call external product. So the external product is a multiplication, a nomomorphic multiplication, but instead of being between 2 ring GSWs as before, it's a multiplication between a ring LWE and a ring GSW. So the operation gives you in output a ring LWE ciphertext. So in practice, you multiply the vector of polynomials times the huge matrix of polynomial, and this vector matrix product gives you, as you might expect, a vector of polynomials. And how do you perform this computation? Well, you perform it in the same way as the product between ring GSWs. So you take your first ciphertext, you decompose the polynomials of the first ciphertext, you have a decomposition, and you multiply the decomposition times your second ciphertext that contains encryptions of the recomposition base, and so it will produce the product that you expect. But now you can observe that this operation is way, way cheaper than the product between ring GSWs, because in ring GSWs, I had to decompose all those ciphertext and do the multiplications with the big one. While in here, I'm just decomposing 2 polynomials in practice and doing 1 multiplication between the decomposition of 2 polynomials and the huge matrix. And this gives me the right result. So the external product, it's still a nomomorphic computation, multiplication, but it's way, way cheaper than the product between ring GSWs. So it's a very, very efficient operation. The only problem is that it accepts ring LWEs and ring GSWs and gives you an output only ring LWEs. So it's not, how can I say, composable in the long term. You always need a ring GSW and a ring LWE, and you transform them in ring LWE. You cannot transform them in ring. So yeah, I think I said everything on this one. So we have an external product between a ring LWE and ring GSW. So to visualize in our mind, before we had matrix product and give us a matrix, this time we have a vector matrix that gives us a vector. So it's very efficient. And so starting from this operation, actually in TFHE, we build what is, in my opinion, the core operations for TFHE, which is what we call the CMAX. So what is a CMAX? CMAX is a multiplexer. Probably some of you know already what a multiplexer is, but yeah, in practice it's a gate that has 3 inputs, B, D0, and D1. And what does this gate do? Well, it applies an if condition. If B is equal to 0, gives you an output D0. If B is equal to 1, it gives you an output D1. So it's an if condition. If 0, do that. If 1, do that. And so this is very nice. And this operation can be evaluated very easily by solving this equation. So you compute D1 minus D0, you multiply times B, and you add the D0. And if you do the math, you will see that the result is exactly what I explained to you 2 seconds ago. So how do we evaluate this operation homomorphically? Well, we can do it by using external product and ring LWE additions and subtraction. So we encrypt D0 and D1 by using ring LWE. So we use the vector of 2 polynomials. We do the subtraction because, well, ring LWE is additive homomorphically, so addition and subtractions are possible. And then we multiply by using an external product times B. And B, we pass it as a ring GSW, so encrypted in a huge, huge matrix. So the result of this external product is a ring LWE vector. And now we can add the ring LWE with another ring LWE D0. And this gives us the right output. So yeah, we use in practice an external product in here to do this multiplication, and the rest is linear operations between ring LWEs. And so now this gate is very, very nice again, because it is an homomorphic if condition. We give you two possible inputs, and depending on the value encrypted inside B, we choose one of the two. And we do all of this homomorphically. And so we use the Cmax to do a very nice operation that is called the rotation. So what I mean for rotation is simply taking a polynomial and rotating the coefficient in the polynomial of a certain number of positions. So if we do it in clear as instance, we have a polynomial with n coefficients, the polynomials that we use in TFHE or in FHE in general. If we want to rotate the coefficients, it's sufficient to multiply the polynomial times x to the power of p, where p is the coefficients that we want to read, right? Actually, this should be p minus 1. There's a mistake in my slide. I think there's a typo in here. But the point is that if we want to read the p coefficient of the polynomial, we rotate times x minus p, and we bring this p coefficient in the first position. So this is a very funny way of reading a coefficient, because you might say, well, if I have a polynomial, if you want to check the p coefficient, I go straight reading to the p coefficient. But in FHE, you have to think about p. Well, p is not somewhere that we can read. You can imagine that in FHE, we have a sort of problem. We cannot read the coefficient, so we can read only the first one. I don't know if you guys know there was a game in television years ago that was called the Wheel of Fortune. Well, the Wheel of Fortune has a huge wheel, and you have to rotate the wheel. And on the bottom of the Wheel of Fortune, there is a little, I don't know, it's like a vertical thing that blocks the wheel. And when the wheel stops, the vertical things point to the element of the wheel that contains your prize in practice. So this will contain price in every slot, let's say, in every slice of the wheel. And you rotate the wheel, and the slice that goes on the bottom, that is pointed out by this metallic thing, is your prize. So in practice, to read your price, you don't know where your price will be. You rotate the wheel and you bring your price to the constant position in practice. And here we're doing the same. Imagine that we cannot read the polynomial. We can only read the first position. So if we want to read the p element of the polynomial, we will bring the p element in first position. This is a little bit how do you have to imagine what we do. So this is very easy in clear. Again, in clear, I should simply go there. But homomorphically, when the polynomial is encrypted, I cannot do anything different. I need to multiply times x to the power of minus p and bring the coefficient in p position in constant position, because the constant position will be the one I will read in the end. So again, in clear and homomorphically works very easily. You just perform a multiplication between your ciphertext and x to the minus p. This operation is very easy to do. It just rotates the coefficient and it does add no noise. But m is encrypted and p is in clear. So what I want to do in rotation is what I call a blind rotation. So not only the message is encrypted, but also p is encrypted. So I want to rotate an encrypted message of a number of positions that is encrypted. So I don't know how many positions I will rotate. So we need to think of a smart way of doing this blind rotation, a rotation that we cannot see. And so the idea that we use is the following one. Well, we take p, and again, we decompose p in binary elements. And so we ask the person that wants us to perform the rotation to provide us the binary decomposition of p encrypted. So we will receive the elements of the binary decomposition of p encrypted in ring GSW format. So we will not see p. We will just see ciphertext encrypting p. And so what do we do to rotate the polynomial m? Well, we will observe the following thing. If I want to rotate m times x minus p, it's also possible for me to multiply m times the different powers, x to the minus p0 to the power of 0, x minus p1 to the power of 1, and so on. X to the power minus pj to at least one rotation. So if I observe m times x to the power of minus pj to the power of j, I also observe that p it's 0, 1. So I have, because we said that this is the binary decomposition of P, right? So P is 0, 1. So I have only two possibilities for this the result. If P is equal to 0, x to the power of 0 is equal to 1, and 1 times m gives me m. So if P is equal to 0, the result of this multiplication is m. If P is equal to 1, I have x to the power of minus 1 times 2 to the j, so x to the minus 2 to the j. And so the result should be mem times x to the minus 2 to the j. And 2 to the j is a quantity that I know, because I know that this is a decomposition in base 2, and so 2 to the j is the clear part. The secret part is pj. So what is this? This is actually an if condition. And an if condition, I can evaluate it, if you trust what I said before, by using a Simux gate. So what does this Simux gate takes in input? It takes in input pj, encrypted under ring GSW, so I don't know pj, and it takes as the two options m, in case pj is equal to 0, and m times x to the power of minus 2 to the j, which is a clear text information, and I can do a clear text rotation, times m, times an encryption of m. And so if the Simux work correctly, well, this selection will give me in output exactly the if condition that we want to evaluate. So it gives me in output m times x to the power of minus pj 2 to the j. So in practice, I was able to evaluate m times x to this quantity that with p that I don't know. So if I want to evaluate x to the power of p for all those things, all those pi's in here, well, it's sufficient for me to chain several Simuxes one next to the other. So I will start from P0, then I will take the result and again do a Simux for P1, then take the result and go to P2 and so on, until I reach P to the k. And so by doing a chain of k plus 1 Simuxes, I'm able to compute x, an encryption of m times x to the minus p. So I rotate m, the polynomial that was encrypted, of p position, where p is a quantity that is encrypted and that I don't know. So this is what we call the blind rotation. Any questions on the blind rotation?
If you have any question, raise your hand and I can unmute you. So meanwhile, I can look at the chat. No, I don't see anyone.
I just have a question. I don't know if you guys are supposed to do a break. I see a question by Siva.
So we usually don't have it, but we give some 10 minutes, 5 minutes time to questions to get a rest, or even if you want. I mean, if there is no question, so we can have it if you like yourself to have it.
Okay.
We had in one case, we had 10 minutes, for example. In Michele's talk, we had 10 minutes break.
In the middle of the talk. I can continue, but it's you guys have had many talks today, so in case somebody wants a break, we can take a little break.
So if you prefer, you think that it's useful, we can take it.
I don't know. Yeah, for me it's the same. Siva, by the way, you have a question. Sorry.
So yeah, it seems that there is a question that can we use MUX as a oblivious transfer for vice versa?
Oh, good question. Can you use it as an oblivious transfer? Well, I suppose it's kind of similar as oblivious transfer, right? You send the two ciphertext encrypted. You need to send everything. That's the problem. But then yes. Wait. Because in oblivious transfer, you have the person that has the answer and the person that is asking the question. So probably you will need to encrypt. It's a good question. If the person that computes the okay, so imagine that you are the person that wants to receive the answer. So you're the person that wants to know the 1 or the 2. I think you need a third party. I'm not sure, but you can use something like this to do oblivious transfer. Yeah, sorry, I need to imagine the protocol, but yeah, you need to set it up properly, but I suppose it can be used to do oblivious transfer. Honestly, I will not use this because it's very expensive compared to techniques we have for oblivious transfer. So yeah, continue using the techniques existing for oblivious transfers, but yeah, I suppose it could be used for that.
Okay, we have another question by Siva. You can go ahead and ask your question.
Yeah. Can you hear me?
Yes, I can.
Yeah. So the P which you decomposed here, and individual bits you have encrypted, right? What about the error? Like how long the P we can like allow? Because the error also gets creeped up, right?
The error, sorry, gets?
Error of the individual bits, like individual ciphertext for the same function, like we need to compute the entire polynomial, right?
I don't understand your question. I hear you very badly. Let me put another air plug. Can you repeat the question?
So there are these ciphertext correspond to individual bits.
The P ciphertext encrypt bits? Yes.
Yes. Then we'll compute the entire polynomial mx, like m0 plus m1x plus m2x square, and so on, like whatever the powers there, right?
Yes.
So the error, there is a danger of error getting increased, and like we might not be able to get.
The error increases. Yes. So the error increases. So if at the beginning you have a small error, it will increase little by little. It's because here you're performing multiplication. So it increases like a multiplication. But yes, in general, external products makes the noise grow, yes. But if we set up the parameters properly, we can perform several external products one next to the other. And actually, the noise in output to the CMUX is mainly depending on the noise of this ciphertext. And these ciphertexts are generally given fresh. So they have the smallest noise possible. So it's those ciphertexts that determine, let's say, the noise growth. And since they have very little noise, the noise will grow really little by little. This is what I can tell you.
Okay, thanks.
But if you want, I can send you a source. So in here, I don't put many details on the noise. I just keep it kind of under the carpet. But we have noise formulas. So formulas that explain you how the noise grows. And you can estimate how much noise do you have in the end. So if you're interested in this, I can provide you sources.
Sure, thanks.
Thank you for the question.
Thank you. So I don't see anything from audience to you as well. So maybe we can continue if you...
Okay. You tell me if you want to take 5 minutes or if you want to stop for 5 minutes.
Yes, we can have a break for 5 minutes. Okay.
Okay. Perfect. Okay, I will try to move quickly then if we start again on the bootstrapping, so we can have the time to do implementation and application. So there are two other operations that I want to talk about before talking about bootstrapping, but I will go very fast on those two because they're really not important to understand what is going on in bootstrapping. So the first one is what we call sample extraction. So sample extraction is an operation that is very cheap that allows us to extract homomorphically one coefficient from a ring LWE inside an LWE. So you take a ring LWE, you choose one coefficient. In our case, we will choose the 0 coefficient, and we can extract it into a LWE homomorphically. So we can do the extraction without seeing anything, and this is a very easy operation. So let's keep it as a black box. And the other operation is the key switching. So again, the key switching, it's very similar to what Hilder described before, probably called it relinearization. So relinearization is a type of key switching. And key switching, what allows you to do is to switch the key, as the name says. So if you have an LWE, encrypted under the secret key S, you can apply key switching and obtain an LWE of the same message, encrypted under a different key. So in order to do that, you need what we call a key switching key. That is an encryption of the secret key S under the secret key S prime. And this is an operation that makes the noise increase, but yeah, it's just used to switch the key in this case. It can be used for other reasons, but for the sake of this presentation, let's keep it like this and let's not check more details. So in order to summarize again what we have after those building blocks, well, we still have our free ciphertext. And now we can see that we can perform an external product and a simux between, well, we had already products between ring GSWs. Now we can make ring LWs and ring GSWs interact thanks to external product and simux. We can perform rotations on ring LW ciphertext, so we can rotate polynomials. We can sample extract, so we can extract one coefficient from here and into a LW ciphertext, and we can key switch. In particular, key switch, we will use it to switch the key inside the LW in the bootstrapping. So in practice, we can make all the ciphertext interact, and we will use these interactions to build the bootstrapping. So how does bootstrapping work? Again, if you remember what I said a little bit more than an hour ago, bootstrapping is the operation that we use to reduce the noise. And the way Gentry proposed to do it is by evaluating the decryption homomorphically in practice. So in TFHE, we can bootstrap only LWE ciphertext for now. Well, we could bootstrap the others, but they rely on LWE bootstrapping. So let's say we can bootstrap LWE ciphertext. And the bootstrapping in LWE, well, we need to evaluate the decryption circuit in LWE. So if you remember the slide minus AISI, the sum of AISIs, which gives you delta m plus the error. And then in the second step, you compute the division by delta and the rounding. So in order to explain you bootstrapping, well, I need to explain you how to evaluate those two steps homomorphically. But instead of starting from step number 1, I will start from step number 2. So I will start by saying that I already know how to compute delta m plus the error. In particular, I will imagine I can put delta m plus the error into the exponent of x, but whatever. So in order to explain you how to evaluate step 2, we need to build step 2, to think about a nice way to evaluate the rounding in practice. So imagine that I have, so the messages that I have, all the possible messages are between 0 and p minus 1, right? So if I put all those messages in clear, now I'm doing everything in clear, as a list inside the coefficients of a polynomial, so coefficient 0, coefficient 1, coefficient 2, and so on. If we use the same idea as the rotation before, well, if I want to access the message m, I will compute the multiplication between this polynomial containing all the messages and x to the power of minus m, and I will bring the m coefficient in first position, which is the way, well, not the way, the place where I generally read my result. So this is the way we read results. The problem is that delta m plus the error is not in 0, between 0 and p. It's between 0 and q, because it's delta m plus the error is modulo q. So I have to imagine if I want to access delta m plus the error, well, I will take all the possibilities between 0 and q and perform a rotation times xm plus the error. So I bring xm plus the error in first position and I can read it. Now, the problem is that in the second step of the bootstrapping, I don't want to read the delta m plus the error. I want to read the rounding, the rescaling and rounding delta m plus the error. So given in input delta m plus the error, I want to obtain in output the message m. So this is a little bit the idea, right? So I suppose I get in input delta m plus the error. I want to evaluate an operation that gives me in output the message m. So how can I do this by using the rotation? Well, I will, instead of putting inside my initial vector all the elements between 0 and q minus 1, I will use repetition, redundancy. So every time one of those coefficients should decrypt to 0, so imagine it's 0 plus 1, 0 minus 1, 0 plus 2, 0 minus 2, they will all decrypt in 0. Well, I will repeat 0 several times. If I have a delta times 1 plus 1, delta plus 1, delta 1 minus 1, I will put 1 in repetition. So to explain it differently, you remember that the torus representation I showed you, and I said that like if you find delta m plus the error that is here in 12, well, 12 is in the slice belonging to 1. So if I found 12, my result should be 1. So in position 12, I will not put 12. I will put 1, right? So in practice, what I'm doing is like I'm kind of opening the torus in some sort of way. I'm cutting at position 0, and I'm really opening the torus to make it become a line. And so in all the position corresponding in 0 position and in all the position up to 7, I will put 0. Then starting from 8, I will put 1 delta times, and then I will put 2 delta times, and then I will put 3 delta times, and then another time 0 just replacing. I'm kind of constructing a lookup table, if you want. Depending on the value I have in input, depending on the value that I found on the torus, all those possibilities, I will replace this value times, by the message corresponding to the slice they belong to. So in practice, I will use lots of redundancy. I build a table with redundancy. And so now, if I want to do again of the operation that I was doing before, well, and I will read the first position, I will start, instead of starting from 0 element from 0 to q, I will start with those redundant elements. So if I compute a multiplication times x to the power of minus delta m, what happens? What happens is that I get exactly in the middle of the m big block. And then if I add the error, well, I will shift inside this block, but I will still go into the message in the big case corresponding to the message m. And so in practice, this is the way we will evaluate the rounding operation. So the step 2, we will try to find a way to compute x to the power of minus m plus error homomorphically, and then we will perform a blind rotation of this lookup table in practice by multiplying times an encryption of x to the power of minus m plus the error. So this is why rotation and simuxes are so important. And so, in order to bring the message in the fourth position, and then with a sample extraction, I will extract this fourth position to spoil you a little bit what happens. So now there is a problem in this approach, and the problem is a problem of dimensions. In fact, this number of elements, it's a q elements. And as I said at the beginning of the slides, q that we use in practice is a very large number. It's 2 to the 32 and 2 to the 64. And the polynomials that we treat in LWE are polynomials to the power of, with n coefficients. And n is very small compared to q. It's like 10 bits, 2 to the power of 10. So we cannot, we have to kind of compress all this information that is in q elements into something that is way smaller. And to do so, we will use an operation that is called the modulus switching that actually Hilder described before. I think I heard him say modulus switching at some point. Well, the modulus switching will select only the most significant part of our message. So in practice, there will not be anymore this problem of q too large, but we will reduce everything. We will compress everything into n coefficients. Okay, so now we know how to do the rotation of polynomials. So we will use this rotation and this lookup table to do the rounding operation. So if we have delta m plus the error, the lookup table will give us in output m. But how do we compute x to the power of delta m plus the error to do the blind rotation? So observe that delta m plus the error was equal to b minus a ISIs. And we can express this operation like we can develop this operation, and this is equal to, well, minus b plus a0s0 plus a1s1 and so on. So we will pass, in order to perform bootstrapping, the s elements, which in TFHE are binary elements, as ring GSW encryptions. And we will try to compute this rotation little by little by using simuxes and stuff that we just saw before. So we give V, which is our lookup table in practice, the one that I just described before that contains all this redundancy. We will give it in clear. This can be also given encrypted, but whatever. And we start performing the rotation of V times this quantity step by step. So we start by rotating times minus b by simply computing v times x to the power of minus b. So b is an element of the ciphertext, so it's something that isn't clear. So we can do this rotation as a clear rotation. It's a very easy operation. And then we start by computing the rotation times AI as i's. And again, since s is a bit, we will simply use a chain of sim-axis to evaluate the multiplication times x to the power of AI as I. And so by performing step by step this rotation, we perform, again, n simuxes one next to the other. And if you follow a little bit the way we described rotation before, or you perform the maths, you will see that little by little, we actually compute what we wanted. So v, which was our initial lookup table, times x to the power of minus delta m plus the error. And now, since this rotation brings in first position the block containing the message m, well, we will extract this block, and this will have performed the bootstrapping we wanted. So starting from an encryption of m, which is the bi ai elements, we are able to find an encryption of the message m. So to summarize a little bit, we take an encryption of the message m, we compute a blind rotation of v, our lookup table containing this redundancy, times x to the power of minus m plus the error. This brings homomorphically the case corresponding to m in first position, and then we use sample extraction to extract the encryption of m. So if at the beginning we had an encryption of m with lots of error, at the end we will have an encryption of m with smaller error. So why? Well, because the error that was in here disappeared thanks to the fact that we evaluated the blind rotation and we extracted the mega case. And the error that comes in here only depends on the bootstrapping key error. And in the bootstrapping key, we will put errors that are very, very small in order for here in the output, having still a little bit of space to perform more computations. So the error in output is completely independent from the error in input. And again, if we choose the parameters on the bootstrapping keys properly, this error will be still small enough to perform more computation. Now, the only thing that can happen is that the secret key after the bootstrapping is changed, is a different key. But again, by using the key switching operation that I was very quick on, we can switch back to the original key S. And so we perform the bootstrapping as we wanted. So now, before moving to the application, there's another thing that is important to notice in this bootstrapping. So in here, I evaluate a rotation of a lookup table, and this lookup table contained repetitions of the message. So in practice, what I evaluated is a lookup table that corresponds kind of to an identity function. But nobody prevents me from setting up the initial lookup table in a different way. So imagine that I want to evaluate a function f that can be tabulated with a lookup table. Well, instead of passing to the bootstrapping the lookup table containing repetition of 0, then repetitions of 1, then repetitions to blah, 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 p minus 1, I will pass a lookup table containing repetitions of f of 0, repetitions of f of 1, repetitions of f p minus 1, where f is a certain function that I can tabulate and express as a lookup table. And so by doing exactly the same things that I did for the bootstrapping, I can actually rotate this lookup table, and instead of obtaining in output an encryption of m, I will obtain an encryption of f of m. So not only I'm reducing the noise, but I'm also at the same time evaluating a function that can be expressed as a lookup table. And this is why very often we call the bootstrapping in TFHE programmable bootstrapping, because we can evaluate the reduction of the noise and at the same time evaluate a function, a program on the input. And this is actually very nice because it opens up for many, many applications. Do we have any question on the bootstrapping? I will try to check the chat. I don't see
anything in the chat. But maybe just to get sure that I got it correctly. So you do the bootstrapping with this programmable technique, and then you also evaluate some function f.
Yes.
But what if this f has multiplications, and why you don't increase the noise again?
Because you don't evaluate. So it's not important how complicated is your function. because you will provide the lookup table of this function. So imagine that your function is, I don't know, square, doing the square. So you know that your possible messages are messages between 0 and p. So you will compute the square of 0, the square of 1, the square of 2, the square of p. And you will provide an input to the bootstrapping, this lookup table containing the result of the square for every possible input, right?
Oh, I see. Okay.
And so then you don't know what the input is, but you can rotate this lookup table in order to select homomorphically the right square corresponding to your message. So it's not important how many operations you need to evaluate the, I mean, of course, this is an offline operation.
Yes,
you can
exactly.
evaluate,
I wanted to say that this you have done in the offline in the lookup table, actually.
And you do it in clear, because you do it on all the possibilities. So you really provide all the possibilities. You do it offline, you do it in clear. So in theory, it should be way more efficient than doing it homomorphically. And you provide already the tabulation. So the only thing that you do homomorphically is selecting the right output in practice. So it's not important homomorphically how costly it was to compute the function. Here you're just selecting something, so it's very easy.
I see. Thank you. I see one more question in the chat. Now it's one more appeared. So the previous one was, can we choose the slices in different sizes related to possibility of messages? May this be useful for error limitations?
That's a good question. So yes, those slices, I suppose the size of those blocks here. Yeah, you can choose them in different sizes. I mean, all of them should have the same size. So, and this size, yeah, let's say it depends on the size of your message. Actually, the size of the interpolynomial is affected by the size of your message. With a polynomial of size 1024, you cannot bootstrap more than 1 or 2 bits of information, even 3 maybe, but not more than this. To bootstrap like messages that are larger, you need larger polynomials. And in those larger polynomials, you fit more slices in here. And the size of the slice depends on the size of the noise as well. So it's parameters depend on the size of the message and on the error as well. Well, error should be always smaller than delta over 2. So this is yeah. But yeah, to answer quickly the question, yes, those sizes may change, may be different, and depend on the size of the message you want to bootstrap. So if the message is really large that you want to bootstrap, this polynomial will be way larger, and you have way more slices to put inside. And I hope this answered the question.
Yeah, it seems there is one answer also to the question by another participant. Thanks, Siva. And that should be okay. Thank you.
Okay, perfect.
We can continue.
Should I continue? Yes. Okay.
Yes, thank you.
Perfect. Okay, so nothing. Another summary slides. So now, apart from all the operations that we had before, we have also the bootstrapping. And the bootstrapping this time reduces the noise. So contrary to the operations before that generally increase the noise or didn't make the noise variate, bootstrapping allows you to reduce the noise, so to bring it back to a lower level. There is another operation in TFHE that is called circuit bootstrapping that of course, I don't have time to describe. And there are other features in TFHE that, again, for time reasons, I think I still have 15 minutes. I will not have time to describe, but if you are interested, I can provide sources or we can discuss them later or separately. So I will move very quickly to the implementation part.
Yeah, maybe there is just one question that you can answer. Yeah, I mean, I guess Siva says that I don't understand how do we manage both those things. Maybe can you clarify?
Size
Siva,
of the range of the function is bounded by n, whereas functional values are from ZQ. All the values, the delta n plus the error are modulo ZQ. So you will compress this operation by performing modulo switching, which in practice cuts part of the error out. So you can reduce it to modulo n, to n actually, instead of modulo q. But n should be larger than p, the size of the message. So it's important that n is larger of p, but is of course smaller than q. Maybe I can go back a few slides to show you this. It was here. So it's this one. So your delta m plus the errors is modulo q, and q is way larger than n. So in order to compress this information, you just cut the last part, the least significant part, in order to keep, instead of 32 bits, 10 bits, right? You had 32 and now you cut to 10 bits. This is not 32, of course, but it's just to give you an idea. So by doing this operation that is called modulo switching, you erase part of the error. Well, the error will increase a little bit in practice, but the important part is that you keep the message intact. And then you will use this modulo switched result to perform the rotation. And the rotation will be done on a polynomial that is of size big N, not Q. Yeah, I don't know if this answers the question, Siva.
Yeah, I don't see any reaction, but I guess yes.
It says thanks. Okay. If you want, we can discuss later if it was not clear. Okay, so implementations. So there are many implementations open source of FHE in general. The two major implementations of TFHE are the TFHE library, that was the one proposed initially with the papers, that only implements bootstrapping for binary gates, so a very special bootstrapping. And a more recent implementation is Concrete and TFHE that we develop actually here at Zama. And they contain all the new functionalities. So not only what was implemented in TFHE library, but more stuff. So we have a programmable bootstrapping for larger functions. So we have various types of data that are treated, not only binary, and there is additional features. And so Concrete in practice is not only a library, it's something more. So to give you a few details, so on the side we have TFHE, which implements the cryptography, and on the other side we have the Concrete. And Concrete builds, uses the cryptography, but also uses additional tools that will help the user simplify his life when he's using homomorphic encryption. Because the point of homomorphic encryption is that it's very hard to use in practice, not only because of efficiency reasons, but because it's very often very hard to find efficient parameters. And in order to find efficient parameters, what we need to solve is an optimization problem on all the parameters that we have. So you might have seen a few parameters. So there are the basis of the polynomial, the modulus, the ciphertext modulus, the plaintext modulus, the noise value. There is many parameters, and every time you move a parameter, stuff move around, and the noise has an impact, and the efficiency has an impact of the operation. So it's like a balance that has many plates, and every time you move one plate, all the others move. So you have to find the optimal organization of your plates. You have to put the right weight in every plate in order to make things efficient. And this is the optimizer that we develop at Zama that takes care of. It will be able to find the efficient parameters, optimal parameters. And the compiler, instead, we will do the translation from the clear text, let's say, circuit into homomorphic in order for the user then to execute homomorphic computations. So in TFHE that you can find online on GitHub, and you have documentation. For now, we have implemented all the operations on the Booleans, so they're very similar to the one that we have in TFHE original library, but we also have operation on small integers. So we have small integers up to 8-bit encrypted into a ciphertext, and we have all the operation to make those integers interact. So addition, subtractions, multiplication, and lookup tables evaluations for several lookup tables. The TFHE offers also other features. It comes with a faster FFT implementation. So by comparing resistance as an example, the fastest FFT implementation in TFHE lib and what we have right now in TFHE, well, we have a reasonable, quite an important improvement in terms of efficiency. So we have a faster FFT implementation. Public key encryption is supported, so you can generate public key to do public key encryption. And we have seeded ciphertext in order to make transmission of ciphertext way cheaper. And very soon, like very, very soon, probably by the end of the month, TFHE will also integrate integer operations that can encrypt larger integers into several ciphertexts, and it will implement also all the operations to make those large integers interact, including addition, subtraction, multiplication, and lookup table evaluation. So if you want to try to use the TFHE, especially with large integers, stay tuned another little while, but you can already experiment with Boolean and short int, and it comes with a documentation, so it should be very easy to use. The optimizer, as I said before, I need to go faster. It's the part, again, that will select for you the most efficient parameters, the most optimal parameters by guaranteeing security up to a certain level that you can provide, correctness of the operations up to a certain error probability, and will guarantees you that these are the most efficient parameter set that you can find. And finally, the compiler, actually, I will go very quickly on this one. It will use the optimizer in order to choose the optimal parameters and the optimal representation of your circuit. It will come with hardware optimization. So in case we have different architectures that we want to develop FHE in, the compiler will give you the better way to transform your circuit to be executed in those architectures. It does the high-level abstraction from the front end and is developed from the MLIR language. So yeah, this is the entire concrete, let's say, framework that we develop at Zama. And again, our goal will be to make things easier for users, even non-expert users, to be able to perform homomorphic computations. So I still have 5 minutes left, so I will go very quickly on applications. I can stay a little bit longer for questions if there is any. For the applications, again, we can use it for many, many applications. We can do a voting. We can use FHE to support multi-party computation. We can do multi-key. We have application that we're starting to develop on a blockchain. You can do every operation on sensitive data, and in particular, you can do machine learning applications. And it will be on machine learning that I will focus the last 2 minutes of my talk, to show you a way of using TFHE and everything I showed you in this presentation to do inference over encrypted data inference of encrypted data. So again, I come back kind of to the scenario that I presented you in the initial slides. And this time I will explicit the function that I want to evaluate on the server side. So the function will be a neural network. And I will send the server the data encrypted, and I would like it to compute the result of the evaluation of the inference of the neural network homomorphically. So the neural network is something that looks kind of like what I'm showing you in the slide. So it contains several neurons that are connected one to each other, and the information passes through the neuron from the input layer, that is this one. The neural network will extract features from your data and will give you the answer to the question you ask. That may be, is this a picture of a cat or a dog? Or is this, what number have I wrote in this piece of paper? Or is there a cancer in this RX that I send you? Yeah, it's many, many questions can be answered. So the artificial neurons, the little neurons that you see, can be of various types, but there are in the very basic neurons, they look something like this. So you put in input, you give in input something that comes from the input or from a previous neuron, like in here. So imagine now we focalize on one of those neurons. So it takes in input elements coming from a previous step, and it computes a linear combination of those elements with some weights, WIs, that are provided on the neural networks, plus this constant bias. And this result will be passed to a function that is nonlinear, and that is called the activation function. So this function, can be various things, can be a ReLU, can be a sigmoid, can be a hyperbolic tangent, can be many, many things, but it's important that it's non-linear function. So how do we evaluate this homomorphically? Well, we can pass all the inputs encrypted. In our case, we pass them as LWE ciphertext. And since LWE ciphertext are linearly homomorphic, we can multiply them times small constant. We can add them together. So we can easily perform the computation of Y. Now, Y is encrypted, and this noise has grown a little bit because we perform homomorphic computations. And now the problem is, what happens if we want to evaluate the nonlinear function f? Well, in the schemes that are leveled, that prefer a leveled approach, the way this function is evaluated is like by approximating this function by a polynomial and evaluating it as a series of additions and multiplications. But of course, this makes the noise grow. In TFHE, instead, we use the programmable bootstrapping. So we tabulate the function f, we pass it to the bootstrapping, and at the same time as we reduce the noise inside y, we evaluate the function f. And so the result is going to be an encryption of f of y with less like if it was an input. And so we can pass this to the next neuron and continue performing this type of operation even for very deep neural networks. And so in practice, we are able yet to evaluate inference of neural networks in a very efficient way by keeping the noise managed all the time. So we have some results. Actually, the results I'm showing you already starts dating from 2 years ago. They were done in 2021. And we were able to evaluate MNIST inference by using a neural network of depth 20 neurons in a bunch of seconds, which is something that is very, very nice in homomorphic encryption, considering that we are evaluating lots of operations and it's really a neural network. So in 2021, we were able to evaluate this in a bunch of seconds. We did experiments in several machines, both on personal computer and also on online servers in AWS. And actually, there is a very recent result proposed less than a month ago that uses concrete again, as we did in these experiments, but proposes way better results, and especially performs not only inference on the MNIST dataset, but also on the CIFAR dataset, which we didn't do in 2021. So I suggest you to take a look on this paper, because they're showing amazing results, and science is progressing and exciting things come out every day. So if you're interested in this stuff, keep an eye open, because many more exciting things are coming. And that's it. I think any other questions, I will be more than happy to answer. Thank you for the time, and sorry for being so late.
No, thank you. That was great presentation. Thank you very much.
Thanks, Karim.
Yeah. I mean, I know that Hilder had one question, so I don't know if you can read it.
I'm reading it. Please, what is the value of n you use to be able to handle 8-bit messages in the programmable bootstrapping? Hilder, I'm very bad with numbers, if I have to tell you the truth, and my memory is even worse. With 1024, I think I can go up to 2-3 bits. I think for 8 bits, we go to, it's for sure more than 4096. I think it's 8,000, the next power of 2, 8,100 something. I don't remember what is the next power of 2, but I think we are around the 8,000. I can double check and confirm it to you. Don't take it as a definitive answer. I will double check and let you know, but I think we are around the 8,000 for n. I see a question for Sophia. How the matrix multiplication is done with the n which TFHE, as it's no support packing techniques. Matrix multiplication? In a neural network. Well, matrix multiplication is not supported natively, but you can express matrix multiplication by doing multiplication between ciphertext and elements in the matrix and then adding them together. So it will be linear operations, particularly several linear operations instead of a true matrix multiplication. Like you do the operation element by element if you want, or you can pack stuff into ring LWE ciphertext and do linear operations, but we need to see the details for this. But yeah, it's possible.
Okay, there's one question and one acknowledgement. So yeah.
Okay, no worries. Thanks. Okay, Hilder. I see a question from FHE2. Hello, Ilaria. For the NNs, are you using quantization-aware training? Second, do you use more loose parameter for in-N evaluation as they allow some small errors? So for the experiments we did 2 years ago, which are different for the experiments we are doing now, and I suppose different from the experiment proposed in the recent paper. I think 2 years ago, I don't remember if we used quantization. I think it was not yet quantization. And we were using an approximated approach. So we were not doing operation over the exact integers. We were using the approximated approach. So we allowed some error to interact with the message and do bootstrapping then. Yeah, it will be different from things that we are trying right now. And again, from the things proposed in that in the new paper that I shared, which is not ours. But again, I can show you the paper and we can discuss about it if you want. How can we use FHE in federated learning? Good question. I don't have an answer. It's a good question. I never think about how to use FHE in federated learning, if I have to be honest. So yeah, I don't have an answer, but thank you for the question because it will make me think about it since I didn't do before. And sorry for not being able to give you an answer.
Okay, I mean, I don't see any raise on hand, so thank you very much. Let's thanks. I mean, Ilaria. Okay,
thank you guys for having me.
Yeah, everyone, you see that loved as we loved your presentation. So there is one more question. Is there a toy example of TFHE to understand the code better? I guess you have.
Yeah, you can actually, if you want to start understanding, yeah, maybe you can start with gate bootstrapping. It's still using are the parameters, but yeah, I can share. There is a blog post on TFHE that maybe explain you with a little toy example. If you want, I can share it with you, and you can take a look. Or if you have any questions, send me an email or contact us, and yeah, we can discuss more about it.
Yeah, I also suggest to check out the Zama's webpage. These days, they are quite active.
Thank you so much.
Yes. Yeah, I mean, they have great materials there. So
yeah, we have a Discord channel. So if you have any questions, also you can post. Actually, there is a channel in Discord for every scheme. So many researchers interact in there and answer the questions. So yeah, if you want to join the Discord channel, it's there's a nice community discussing in there.
Perfect. So thank you very much. Maybe we can end up the session and also thank the Ilaria. I mean, great presentation. The presentation.
Thank you so much for having me, guys. It was a pleasure.
No, it was our pleasure. So yeah, thanks everyone. So this is the end of the session, and we will continue tomorrow with the applications mostly. Thanks, Ilaria. Okay, have a nice evening.
Thank you, guys. Thank you. Bye.
Bye.